Okay. Here we go. Chapter 6 is the thermodynamics chapter. It is the enthalpy chapter, the dreaded enthalpy chapter, if you remember. What is this? I probably didn't give you your notes, huh?
Yeah, that'd be helpful.
Yeah. There it is. There it is.
There's a lot of problems.
What did you say?
And I have a second one trying to finish my brother. That's probably you're just worried about MLA means double space, both point, Roman, hence the Roman.
World, what do I do with it? There it is. All right, so we're going to talk about thermodynamics in this chapter, which is heavily dealing with energy, but usually in the form of heat. Okay, so if I were to say there was a big overarching theme, it's energy revolving around heat transfer. Okay, we're going to kind of talk about quite a bit of things today. A lot of vocab. More conceptual stuff. At the end, we get to some of the math-related things. Okay, but really, energy is the very essence of our very existence. If we don't have energy, really, I mean, we don't have God, we cease to exist, but like, we need to have energy to exist. Okay? Energy is everywhere. Every living cell is like a mini chemical reactor in our bodies. I mean, it is just powered by energy through chemical reactions. So, if you remember, energy is kind of an elusive term. You remember how we define energy without looking at your notes?
The ability to do work.
Yeah. The capacity to do work, or we could say, we haven't really talked about this much, but we're going to specifically talk about it in this chapter because it's very heat dependent, or the ability to produce heat. Now here's quite a few vocab words that you should remember. Potential energy, just due to position or composition, and composition is going to be probably our bigger factor here in this particular chapter and in chemistry, because when we talk about potential energy, it's usually revolved around the potential energy stored up where?
Chemically.
Where would the potential energy be stored up chemically?
In
The bonds.
oh.
Okay? And then you guys are all familiar with kinetic energy being energy in motion. There's your kinetic energy equation. I'm not sure if you'll need that for your homework, but I gave it to you just in case. But I feel like you guys probably understand the difference between potential energy and kinetic. I know there was like a little visual, but are you guys good with kinetic and potential energy?
Yeah.
Okay. Potential can be converted to kinetic and so forth. And a lot of times that's what happens when we're talking about heat, is you got potential energy stored up in bonds, and when that potential energy changes, it usually changes to kinetic energy in the form of heat transfer. Because we know temperature has a lot to do with kinetic energy, correct? Okay, so there's a lot of stuff that's stored up in bonds that's going to be changed to kinetic energy in the form of heat transfer. Okay? So heat, now remember I spent quite a bit of time in regular chemistry talking about how heat isn't something an object has. It's essentially something an object can do. Okay? And so heat will transfer only under certain conditions. Heat will not transfer if you don't have a difference in temperature between two objects. If I got two objects touching each other and they're the exact same temperature, you cannot say this has a lot of heat. Okay? Heat is the transfer of thermal energy that is stored up in the particular system due to a temperature change or a temperature difference. You guys should know this. Heat or energy always is transferred from hot to cold or cold to hot. Hot to cold every single time. Okay? So when you open up your door to your house in the winter, it's not that the cold air is coming in, it's that the warm air is going out, which therefore lowers the temperature on the inside.
Also, would it be cold air flowing in?
Whatever, I was just trying to prove the point. Okay? Work. Now the only one of you that probably knows anything about work other than what I told you in physical science is Emily, because she took physics. But work is really a force acting over a distance. Now here's something that's important that you may or may not have in your notes. In order for this to be true, the force has to be in the direction of your distance / motion. So when they're talking about a force over a distance, it's really talking about a force that causes an object to move a certain distance. Okay, this is where it can kind of get tricky, but if I'm applying a force perpendicular to the direction the object's moving, that force is not doing work. Let me state that again. If I'm applying a force that's perpendicular to the motion of an object, that particular force is not causing work. It's actually going to have to be a different force that's doing it. So like if I were carrying actually here. I don't know. There's two situations. If your force doesn't cause a motion or a movement at all, no work is done. For example, if I push on this wall as hard as I could, you'd think I'm doing physical labor, so therefore I'm doing work, right? In the context of what we think work is, it's different than physics work. Okay? So I'm not doing any work on that wall because the wall's not what? Moving. Okay? Same thing if I lift the chair up and hold it right here. If it's not moving, I'm not doing any work. I know it's kind of weird to think about. Now, did it take work to get it up to that point? Yes. Okay? If I'm carrying an object, and say I'm holding a bucket. Kind of difficult, but if I'm holding a bucket, and I'm moving this way, my hand is not doing work on this particular chair. Because my hand, assuming I'm holding it straight perpendicular to the motion, which way am I moving? That way. And the force holding the chair is up. Okay? So really it's the result of my feet pushing on the ground that's causing this to go, not my hand holding the chair. Okay, so if an object is moving, work has to be done, but it may not be due to the force you think. Okay, so always remember, if work is never done, if the force you're looking at is perpendicular to its motion. Okay? It's going to become, it's more important in physics, but I just wanted to allude to that today because it does have some significance. So, quite a few vocab words there. Oopsies. All right, this starts getting into some really abstract thinking. I remember talking about state functions in my capstone chemistry class as a senior in college. Now, we're just introducing it. We're not really going into detail about state functions. Okay, but here's what essentially this is. A state function is really a property that's independent of the path. Okay, if you remember when we did the thermodynamics chapter in regular chemistry, we talked about enthalpy. And do you remember me drawing a picture or visual of the mall, and you went into the mall and you went into different buildings or different stores and then you left the mall, and the whole purpose of that was to show you the difference between path dependent and path independent. Do you remember that? So at least vaguely? Okay? So what a state function is going to be something that's independent of the path. So really all you're worried about is the initial and final positions, and that's all you need. Enthalpy is one of those. okay, it's a state function. Doesn't matter what the path is. Okay, another thing that doesn't matter what the path is overall energy. Okay, here are two things that we're going to spend a good amount of time talking about that do depend on the path. Work depends on the path, okay, and heat depends on the path. Those are not state functions. Is that in your notes at all, that work and heat are dependent on the path? Okay, so you would say, you could write an arrow next to it saying those are not state functions. So a state function does not depend in any way on the system's past or future. The value of a state function does not depend on how the system arrived to its present state. It depends on the characteristics at its present state. Let me give you another couple examples of state functions that might make a little bit of sense. Okay? Elevation versus distance. Elevation is a state function. Okay, so I could say Chicago has an elevation of 674 feet and Denver has an elevation of 5,280. How I get from the elevation of Chicago to Denver would be your distance, right? But regardless of how I got from Chicago to Denver, did the elevation change? So elevation would be a state function. Does that make sense? Doesn't depend on how you got from Chicago to Denver, because the difference in elevation is the same no matter what. Okay? State function. Distance would be not a state function, or would depend on the path, how you got there. Right? Oh boy, more vocab here. Most of the stuff you know though. System. The reason why I bring this back up is because a lot of stuff we're going to be doing, it's really important to recognize what your system is and what your surroundings are. When we do work, we need to know when we're talking about a piston, applying a pressure on something, what's your system and what's your surroundings. It's very, very important. System is simply what you have chosen to focus on. You can make the system whenever you want. Okay? But whenever you set your system, you got to stick to it. And then surroundings would essentially just be what? Everything else. Okay, I don't think that's too difficult of a question. Okay? So if I was talking about a piston applying a pressure on, let's say there's some fluid in there or some gas, I could say that is my system. Everything else, my piston is my surrounding. Everything else would be my surroundings. Exo and endo here. You know this, you're familiar with it, but we're going to talk about where this energy comes from and where this energy comes from. We know exo's energy is released, and we know endo energy is coming in. Where do those come from? Because we know there's a certain law called the first law of thermodynamics that states that it had to come from somewhere, right? Can't be created or destroyed. I like to squish crickets because they get really juicy.
Use the paper towel. Do you need me to kill it?
No.
It's out of my training visual now. Okay. Stop looking at it. Okay. Here's the question I have then. We got an exothermic reaction. Where does that energy come from?
Chemical potential energy in the product. Chemical reactions.
Okay, chemical potential energy. So what we're going to spend on this next slide is really something that, let me see, this is important, I think this is what he said. This is something that I think is really, really valuable, and a lot of times we mess up. when we talk about bonding, things bond to become what? Stable. Okay, but what does stable mean from an energy standpoint? Low energy. Okay, that is very important. Here's another thing that most people don't make the connection on. High energy means weak bonds. They're unstable bonds if you have high energy. So actually really easy to break because they already have high energy. Does that make a little bit more sense if I say it that way? Low energy actually means strong bonds. They're stable. Stable, low energy are your stronger bonds. Okay? So let's think about this. Is there another? There we go. Let's think about this particular reaction. What's going on? Got my reactants, I got my products, and I'm going to draw, if you remember this from regular chemistry, an energy diagram where we go, it goes like that. Your reactants, your products. This would be an exothermic reaction. Why is this exo?
Energy is
Released, right? So when I go from reactants to products, my overall energy goes down, energy gets released to the surroundings. Okay? So here's what's really happening here. My reactant bonds here, these guys have to be less stable. For the most part, things react because they want to become stable. So these guys are less stable, they have much higher energy, there's more energy stored up in their bonds, and so they're easy to break because they're unstable, high energy bonds. Does that make sense? Okay? So, because remember, when we're looking at energy, it's really a difference between the two. Because does it take energy to form these bonds? Or to break these bonds, excuse me? Yes. But it doesn't take very much energy because they're weak and they're already at a high energy. Okay? When I form my stable bonds, okay? Stable bonds are low energy bonds. So it only takes a little bit of energy to form them. Or, a little bit of energy to form them. And so really there's a big difference from the amount of energy I had in these guys and far less energy here because it's stronger stable bonds, lower energy bonds. Well, do you see the difference in energy here? Much more energy in my reactants. Far less energy in my product. Well, where does the excess energy go? Yeah, it's released as an exothermic, in an exothermic form, in the form of heat. So, chemical potential energy that was stored up in these bonds got released in the form of heat that got given to the surroundings in this case. Right? It's really important to be able to understand. Little energy goes into breaking bonds, lots of energy gets released because you're forming strong, low energy bonds. All right. Really important here. I want to focus on this bottom part. Okay, there's just your definition of thermodynamics. Not overly, important. Sure, we need to know what thermodynamics is. It's just really the study of interactions regarding heat energy for the most part. You know the first law of thermodynamics already. Internal energy is a little bit tricky. It's really a particular property of a system that can be changed based on heat flow or work. Okay, and you've got an equation there. So the internal energy is referring to energy of a system. Okay, the energy of a system is really dependent upon Q. Do you remember from regular chemistry what Q represented? Remember that Q? This is the calorimeter equation. We'll do this chapter. That's the calorimeter equation. Q is heat. And W is a little bit easier. What is it? Because we said that energy can be changed one of two ways, in the form of heat or in the form of work. Now, again, since Emily took physics, this will be what we're doing today is a lot of physics stuff. Okay, but it's physics and chemistry are pretty related. Sign conventions are so important. Okay, when you add or subtract, all you're doing is moving a direction. So what a sign does is simply tells you a direction. Okay, in physics we talk about how a positive can be north or it can mean east. A negative is south or it is west. Okay? Well, let's think about this. When we're talking about energy, exo and endo, it's the same amount of energy, it's just one is leaving and one is coming. So mathematically, we have to come up with some sort of sign convention to say, is positive mean leaving or does positive mean coming? Does that make sense? Here's the sign conventions that they use. Now, the endo and exo agrees with what we've talked about in chemistry. If you remember, we talked about the change in H when it's positive and change in H when it's negative and things like that from last year. Okay? The work one for you is going to be a little bit different. Because it's different from what we did in physics. But here's what positive means. We're going to look at all of these sign conventions. Our reference point is going to be the system. Could I have chosen the surroundings as my reference point and had a positive or negative be dependent upon what happens to the surroundings? Could I have done that? Yeah, I could have. Makes more logical sense to do the system though. Okay? So a positive means, because we got to know what positive means for heat, we got to know what positive means for work. Positive means endothermic, because we know what's going on with heat or heat energy?
It's taken in.
It's taken in. So the system is gaining energy. Does that make logical sense why we choose a positive when the system's gaining energy?
Yeah.
And it would also then make sense that exo, the system is losing energy, right? What's gaining the energy in this case?
Surroundings.
The surroundings. Okay? So since we're talking about it from the system's perspective, the system's losing it. If I were talking about it from the surrounding standpoint, I could say the surroundings is gaining it, but we're only going to focus on the system. Okay? Second thing. Work, a little bit trickier. Okay? Positive work means that the surroundings are doing work on the system. Let me show you what I mean. This would be an example of, let's say I got my piston here. Okay, let's say that's my system. And everything else is the surroundings. Okay? If the piston was pushed downward, am I doing work on the system or is the system doing work on the surroundings? What do you think? Doing work on the system, so that would be a positive work. Surroundings doing work on the system. Positive work. What if the gas expands and causes the piston to go up? Now it's negative work, because work is leaving the system, it's being acted upon on the surroundings, therefore a negative work in that case. Okay? This is really important because the math problems we're going to do today, you need to put a positive sign or a negative sign on it based on what it says in the context of the problem. Because it won't say, the work is negative this. It'll say, the piston or the gas did work on the surroundings. And you got to realize, oh, that means negative. I got to put a negative on that. Okay, I'll show you what I mean. Let's see this first problem. This one's not overly difficult, but I'll just show you what I mean. Okay, calculate change in E. So here's your equation. E, what? E is dependent by the Q or the heat and the work. Okay, it says for the system undergoes an endothermic process. Now notice, it didn't give us positive or negative Q, did it? We have to know that endo means what? Positive. What if it said it was undergoing an exothermic process? You'd have to plop a negative on there. It's not going to give you the negative. Okay, so you have to read these carefully. So we know our Q is going to be 15.6 kilojoules. I realize that this problem is just simply adding, but I'm trying to point out here that there are words in here mean something. Okay? And where 1.4 kilojoules work is done on the system. On the system, is that positive or negative from a work standpoint? Again, still positive, but could it have been the opposite? and you have to then have plopped on a negative with that. I know you guys know how to add. Okay? The system gains that much energy because all the stuff was given to the system, right? Alright, let's do this one. I'm going to give you another equation for this. Okay? Only Emily will have seen this equation probably. But it should make sense based on the definition I gave you for work. Work is force over distance. Alright? Okay, well if you look up here, it tells me nothing about force, does it? Okay? It also really tells me nothing about distance either, does it? Okay, so let me give you another equation that's also pretty important. We know that pressure is a force over an area, correct? I'm going to manipulate that for force and plug into this equation. So force would be pressure times an area, correct? I'm going to take that, I'm going to plug it in here. So work is a pressure times area times distance. This is not your final equation yet, just letting you know that. What's an area times a distance? We can simplify those two variables into one. What's an area and times a distance? What's area? How do you find area? How do you find area? When you're doing math, how would you find the area of a square? Length times width. Add another side. What do you get? Which would be volume. Okay. So your equation that you want, and I'll explain here in a little bit why this needs to be a negative. You want that guy. You can have this. It wouldn't be bad to have this because it's possible they might give it to you in form of area times a distance. So I wouldn't say that it's awful to have the previous one. You want this one. You want this. I mean, you really, I suppose you probably want all of them. But
It's negative.
yes, and I'll explain why. Well, I may not have time to explain why, but in a nutshell, essentially why they put a negative is so that mathematically it works out based on the sign conventions that we chose. So I'll show you what I mean. Well, let's just do this problem. Okay? It says calculate the work associated with the expansion of a gas. All right, so we're expanding a gas. First of all, what does that tell you about? Should tell you about your work sign. Okay? At a constant external pressure. So work equals negative 15 atmospheres. Change in little delta there, if you're not familiar, is just final minus initial. So it'd be 64 minus 46. Now, if you plug in and you solve, you'll get a number that is negative. Which, what is it? I don't appear to have an answer here, which is stupid. Oh yeah. Negative what?
Negative 140. Is that right?
No. 270.
Yeah, just negative 270.
Now look at the units. They're kind of an interesting unit. But I want to show you something here. That's actually, we can turn that into a unit that makes more sense here in a sec. But notice we have a negative work. The reason why this equation needs a negative is to fit our sign convention. If we think about what's going on here, we're expanding the gas, which would be doing work on the what? Surroundings, right? If a gas is expanding, it's pushing up on the piston, doing work on the surroundings, and is that a positive or a negative work? Negative. We need it. If I were doing the opposite, if I were compressing the gas and these two numbers were flipped, your change in V would be a negative number, correct? A negative times a negative would give you a positive, and would that make sense based on compressing a gas being system work done on the system, positive. You see what I'm saying? That's why that negative's there. It just poof out of thin air. They do it based on our sign conventions so that it works. Okay? Now, here's one thing you'll want. 1 liter times an atmosphere is equivalent to 101.3 joules of energy. That's going to be pretty valuable because we think of energy usually in the form of joules, correct? Is it possible that they could ask you to figure out the work in joules and you have to then take the atmospheres times a liter, use that as a conversion factor and solve for joules? Yeah? Make sense? Okay, let's do the last problem. Questions so far? A lot of stuff today. Alright, a balloon is being inflated to its full extent by heating the air inside it. I'll do that. In the final stage of this process, the volume of the balloon changes from that by the addition of so much energy as heat. Assuming the balloon expands against a constant pressure of 1 atmosphere, calculate the change in E for this process. So, we need to find change in E. What of those 2 variables did it not directly give you? Work. It directly gave you what? Okay, so we know Q. Now let's look at the context here. By the addition of 1.3 times 10 to the 8 joules of energy. Is that going to be exo or endo? Endo, so it has to be positive. Good, we do not know work, but we probably have enough information up here to figure out what the work is. What is our pressure here? What is our pressure? 1 atm. Okay, now let's just look at this. Changes from this to this. So there's your initial, there's your final. When your final is bigger than your initial, then my guess is that your work will be what? What are we doing? Are we expanding or are we compressing? Expanding, which means work's going to be done on the surroundings, right? You're expanding, you're pushing the piston out, doing work on the surroundings. Okay, so it will end up being a negative. Okay, so when you figure out your change in volume, I think it's 5.0 times 10 to the 5th. Which will give you negative 5.0 times 10 to the 5th atmospheres times liters. Great, I found the work. Can I take the work and plug it into here and solve now? Yeah, it needs to be in joules because you cannot add units that aren't alike. Colin? Take this, convert to joules. 1 atmosphere times a liter is 101.3 joules. For the sake of time, I'll give it to you. Negative 5.1 times 10 to the 7th. To finish then, we plug into our internal energy.
Whoa.